fall series of PIRE webinars, Astrophysics Empowered by the EHT. I invite everybody to check the full schedule. We have one more coming up on general relativity by Emanuele Berti, and please register for that future webinar as well. You can also view the past webinars, the entire series, if you missed them, on our YouTube channel, Black Hole PIRE Science channel. So you're more than welcome to look at all the past webinars from this series, as well as the ones that the Black Hole PIRE program has hosted in the past. This is our educational component of an international PIRE project, and we really value your feedback, and we use it to make the future webinars better than what they are right now. So we really, really appreciate it if you take 2 minutes at the end of the webinar to provide your feedback about what you liked and what could be improved. We are sharing that link right now in the chat window. So again, it just takes 1 or 2 minutes, and we use your feedback to make changes to our program. Please turn off your audio to avoid background noise. This is especially for the panelists, and I will be turning off my video after I introduce our speaker today. And it is my pleasure to welcome Eliot Quataert, a colleague and a friend for a very long time. Eliot is a professor of astronomy and physics at Princeton University, and he has actually just moved there from UC Berkeley, where he was most recently the chair of the astronomy department, as well as the director of the theoretical astrophysics program. He's an astrophysics theorist who works on a broad range of problems. He's very versatile. He works on stars, black holes, plasma astrophysics, and the formation of galaxies. And he has received a number of national awards for his research, including the Warner Prize from the American Astronomical Society. He had a Packard Fellowship, a Simons Investigator Award, and he has been recently elected to the American Academy of Arts and Sciences. He's also a fantastic teacher, so we are very lucky to have him today as part of our webinar series to talk about accretion disk plasma physics. Thank you, Eliot, and I will be moderating the questions throughout your webinar, and you can also see them in the chat and the Q&A.
Great, thank you, Ferial. So thanks everybody for joining this morning or evening, depending on where you are. So what I'd like to do today is to try to tell you a little bit about some of what we know and some of what we don't know about plasma physics related to accretion disks, in particular in the context of the EHT. Please do feel free as we go to ask questions. Don't feel you need to wait till the end. I'd much prefer you to get your questions answered kind of on the fly. Okay, so I'm going to start just by reminding you a few basic things about accretion disks and about sort of the energetics of accretion disks to set the stage for why we're interested in these questions about subgrid plasma physics and what that really means in the present context. And a lot of the general motivation at the beginning could apply to a wide range of disks around young stars, luminous disks around supermassive black holes, but I'll focus in particular on the questions in the context of the EHT sources like the Galactic Center and M87. And then hopefully at the end, I'll give you a sense of where I think some of the progress might come in this area. So there's some general properties of accretion disks that we can infer from mass, angular momentum, and energy conservation. And I know that Ramesh went through these in his webinar, but I still want to make sure we're all on the same page by quickly going over that. So matter in a rotating accretion disk is to first approximation on circular orbits with a slow inward drift due to the redistribution of angular momentum outwards. It's that transport of angular momentum that allows the material to flow in. In general, the inflow time is longer than the orbital time. And that inflow rate, we think, is mediated by magnetic fields, either the magnetorotational instability or large-scale magnetic fields that are more like winds from the accretion disk, torquing the material and allowing it to flow inwards. The energy released by the virial theorem to go from some large radius to radius r is half the gravitational potential energy. And if you make it all the way to the innermost stable circular orbit of a black hole, that's tens of % of the rest mass energy of the accreted material. And we think that in accretion disks, the properties of the disk depend critically on what happens to that energy that's released. And that's dictated basically by a comparison of the cooling time scale. How long does it take the plasma to radiate away the thermal energy that it has gained via flowing inwards, this energy released, compared to the inflow time? If the cooling time is short compared to the inflow time, the material sort of collapses down into a thin structure. If the cooling time is long compared to the inflow time, then the material retains all of its thermal energy as heat, and that heat is advected inwards or outwards, inwards into the black hole, outwards in an outflow. And so that distinction between radiating efficiently or radiating inefficiently sort of divides up the types of accretion disks that we have. Thin disks, as illustrated in the sort of schematic from a paper in the 70s, right? Those are relevant when the energy is radiated away efficiently. That's what happens in star and planet formation. That's basically what galactic disks are. And that's what we think happens in luminous black holes and neutron stars. Thick disks, where the energy is stored as heat and it's advected around in inflows and outflows rather than being radiated, that's basically relevant to to low luminosity compact objects, including EHT sources. And this is also relevant to super Eddington accretion, when the energy is trapped because it can't random walk out by diffusion before the material falls into the black hole. Okay, so now to talk a little bit more about the energetics of disks to set the stage for what we really mean by the kind of subgrid plasma physics. The ultimate energy source in accretion is the gravitational potential energy and the energy of differential rotation of the material that's spiraling inwards. And we think that that energy source is tapped by magnetic fields, by local instabilities, the MRI, or large-scale magnetic fields that torque the disk and extract the energy of the inflowing material. And the energy thus goes from gravity and differential rotation into magnetic fields and turbulence, and it then has different channels that it in principle could go into. The energy stored in the magnetic field and the MHD turbulence could go into thermal energy of the disk, or it could go into not the majority of the mass, but a small amount of the mass that might be something more like a corona, analogous to the corona of the sun, or the energy could actually be redistributed over very large distances, right? In jets, energy extracted from the central source, the accretion disk in the black hole, is redistributed by Poynting flux over very large distances. And these are different ways that the ultimate energy, gravitational potential energy and differential rotation, can be converted into different forms. Thermal energy of the majority of the mass, the disk, thermal energy of a small amount of the mass, the corona, or it can be redistributed over long distances by waves and Poynting flux. And which of these is sort of the dominant energy channel determines what the disk looked like. It determines the radiation that we see, and it determines the properties of the outflows, the jets and the winds that the disk produces. So we really need to understand these different energy channels in order to understand both the structure and the observational appearance of accretion disks and jets in all astrophysical environments, and in particular in compact objects, which is what I'm focusing on here. And in some ways, the microphysics or the subgrid plasma physics of the title of this webinar refers to almost everything in this diagram. It really refers to how is the energy that's stored in the magnetic fields and the MHD turbulence, how is it distributed into these different channels, and how does that give rise to the observational manifestation of the accretion disk and the jet. And so an analogy that might be useful is to stars. So these are some observational images of the sun. The upper left is a white light image where you're seeing the thermal energy of the photosphere. The lower left is the corona of the sun, which is much patchier. The upper right is a patch of the surface where you see the convective cells. The bottom right is a movie where the sun is blocked out and you see the corona and solar wind. And the same set of questions about energy flow in stars has been studied for over centuries. We now know that fusion is the ultimate energy source. That energy goes into radiation, which in the case of the sun then goes back into convection at the surface. And almost all the energy in convection goes back into radiation, producing the image we see in the upper left and the upper right. But actually a small fraction of the energy in convection in a star like the sun instead goes into waves and magnetic fields. And those magnetic fields and waves power the chromosphere and corona and solar wind. Those are subdominant energy channels in a star like the sun. A part in 1,000 of the energy goes into the chromosphere. A part in 1,000,000 goes into the corona, shining in X-rays, and a little bit less than that goes into the kinetic energy of the solar wind. I think it's sobering in thinking about the energetics of disks that there's actually a fair amount about the energetics of the sun that we still don't fully understand. NASA launched Solar Probe, now called Parker Solar Probe, precisely to try to answer these questions by going close to the corona and measuring in situ what's actually happening. We also know that in different stars, the energy channels that I've shown here operate differently. In massive stars, fusion energy goes directly into convection in the core and then into radiation in the surface layers. And those different ways that energy flows in stars is responsible for a lot of the observational differences of different types of stars, different mass stars and stars in different stages of stellar evolution. And just like we understand that sequence of different stars as a consequence of the different energy flow in stars, we'd really like to understand how differences in the energy flows in disks give rise to the diversity of observational manifestations of accretion disks around black holes, white dwarfs, normal stars, etc. And our understanding of what happens in disks is less advanced than it is in stars. So this continues to be, I would say, a much more challenging field where there's still a lot of opportunity for progress. Okay, so that's a little bit about the background to set the stage of what we're talking about. And I now want to really focus in on thinking about the energy flow in the context of EHT-like sources. So before I go on, let me just pause for a second and see if there are any questions about that sort of overall background of the basics of accretion disks and overall energy flow in disks. Any questions on that material? Okay.
I don't see anything in the Q&A or the chat right now.
Okay, well, we'll keep going. Feel free to ask questions as we go. So I want to focus in now on what we think is going on in EHT sources, M87, the galactic center, similar accreting supermassive black holes, and why some of the questions that I framed rather broadly to start are important in that context. So to set the stage, I want to remind you of something from Ramesh Narayan's webinar again, that we think in systems like the galactic center in M87, the mode of accretion is this geometrically thick, radiatively inefficient, advection-dominated flow. And that's because the accretion rates are rather low. Low means low compared to the Eddington accretion rate. And in that regime, cooling is relatively inefficient. And that means that the basic energy flow of the disk is that gravitational energy goes to thermal energy, but that thermal energy isn't radiated. So something like, for accretion onto a black hole, as we're interested in here, something like 10% of m dot c squared goes into thermal energy, but that energy isn't radiated away. It's instead stored as heat. And since the energy isn't radiated away, a good rough estimate of the temperature of the plasma is that the thermal energy is comparable to the gravitational potential energy. That's just because gravitational potential energy tapped by magnetic fields, as I described, that's the ultimate energy source for the disk. If that energy isn't radiated away and goes into heat, then KT has to be about the gravitational potential energy of a proton that's accreting onto the central black hole. And that means the temperatures we're talking about are extremely high. The temperature near the event horizon at a radius about the gravitational radius might be 1 trillion Kelvin or so, GeV type temperatures. That's the natural temperature scale close to the horizon. And at that temperature, and at the low accretion rates of interest, it turns out that the Coulomb collision time between electrons and protons is very, very long compared to the time it takes the plasma to flow onto the black hole. And so the material that's flowing onto the black hole is actually completely collisionless in the sense that Coulomb collisions don't have time to exchange energy between electrons and protons before the material falls onto the black hole. And what that means is we need to be a little bit more careful when we say the temperature is 1 trillion Kelvin. Well, the temperature of what, right? If there isn't time for Coulomb collisions to redistribute energy and force thermal equilibrium, then there's no reason that the electrons, the protons, the helium nuclei, the iron nuclei, whatever you're interested in, there's no reason that those species have to have the same temperature. And indeed, we think that in general, in the types of systems that the EHT is observing, the proton and electron temperatures are probably different. And how different they are is one of the big questions that we're trying to understand theoretically and observationally. But the general thinking is that probably the proton temperature is somewhat larger than the electron temperature near the black hole. But whether somewhat larger is a factor of few or a factor of 10 is still a very active area of research, both observationally and theoretically. And I want to stress that I've sort of posed this here, this inference of high temperatures and very slow collision time, so the system is very far from thermal equilibrium. I've posed this sort of theoretically, but this is something that can actually be inferred directly from the observations themselves. So just to take M87 as an example, so the left here is the image of M87 released by the EHT, showing synchrotron radiation from relativistic electrons close to the event horizon of the black hole. And from this image, we can roughly infer the physical properties of the material that's producing this synchrotron radiation. We can measure the synchrotron flux, the frequency that most of the synchrotron radiation comes out at, which is millimeter wavelengths or hundreds of gigahertz frequencies. And we can measure the size of the emitting region. The size of the emitting region is about the size of the event horizon of the black hole, because that's the scale of the image. And given those observables, one can actually estimate, just from the observed properties of the system, one can estimate the physical properties in the accreting plasma. The magnetic field strength is several to tens of Gauss. The electron density is probably a few times 10 to the 4 particles per centimeter cubed. And the electron temperature is probably 10 to the 10 Kelvin or so. That's a few MeV. And the electron temperature is probably a lower limit that I've estimated here, because we don't know exactly the size of the region where the emission comes from. And that's actually a good thing. The size of the emitting region is small, which is the reason that the EHT image is so strongly affected by gravitational lensing and Doppler shifts. And that's why this image has the characteristic properties it does. So from this magnetic field strength, density, and temperature, one can infer the properties of the plasma. And what one infers is that there's a hierarchy of length scales in this system. The Larmor radius that describes the gyration of the electrons and protons around the magnetic field, the Larmor radius is very, very small compared to the size of this image. So it's much less than the event horizon in size. But the Coulomb mean free path, due to collisions between particles, is very large compared to the event horizon. So that's sort of the hierarchy of length scales. Larmor radius is small compared to horizon, which is small compared to the scattering Coulomb mean free path. And what that means is that the plasma we're dealing with is this very low collisionality plasma, like I alluded to on this slide here. Okay, so there's a question on chat now. Besides collisions, what other mechanisms are there to exchange energy between protons and electrons? And that's actually one of the significant theoretical uncertainties that we still don't have a great handle on. And so that's actually an active area of research. So the most likely culprit, and I'll come back to this in a few minutes, the most likely culprit would be energy exchange between electrons and protons, or really, in addition, energy exchange among the electrons themselves and among the protons themselves, mediated by the magnetic field, so mediated by electromagnetic fields. And how efficiently those operate is still an active area of research. I would say, in particular, how efficiently those operate between electrons and protons. Are there ways of taking thermal energy of protons and giving it to the electrons, not by Coulomb collisions, but mediated by the electromagnetic fields? This is still a big uncertainty in our understanding of these plasmas in this environment. So we don't have a great handle on how efficient those processes are. But that's a good question that gets at one of the uncertainties that I'm alluding to here at the bottom, by saying there's a lot we don't understand still about trying to model the plasmas in these environments. Okay. So let me remind you about why the fact that this plasma has this hierarchy where the mean free paths are long, the plasma is pretty collisionless. Why does this introduce uncertainties? So then there's a follow-up question. The protons, is there a radius at which the protons fall in faster? And is there thus a net charge in the plasma? There's always a small amount of net charge which is just the net charge required to generate the electric fields that produce currents and that produce the magnetic fields in the plasma. But we think the net charge is extremely small, and it can just, meaning the local charge density is much, much, much less than the density of the plasma times the charge of an electron. So the net charge is probably not dynamically important, and it's really just what is required to generate the electric fields that are there. But it's not a dynamically important charge. So this is very different for anybody out there who knows a bit about pulsars, where you can have charge separation. In the majority of the accreting plasma, we don't think there is charge separation. The electrons and protons are roughly charge neutral. The exception to that is in the vicinity of the jet, where the densities are much lower and there may actually be charge separation like in pulsar magnetospheres. But that's not true in the bulk of the plasma. So just to kind of go back to this, astonishing EHT image, which has generated all of this interest and a huge amount of work, the EHT papers had a very impressive theoretical modeling effort, which went into trying to interpret what this image was telling us. And all of the models in the EHT papers, and indeed the majority of the models that are in the literature that are trying to make sense out of accretion in M87 and the galactic center and systems like that, they are fluid models. So they're based on GRMHD, which is a fluid theory. And Charles Gammy in his webinar described a bit about that theory and described how it's implemented numerically. And they're moreover one temperature GRMHD, because normal fluid theory, magnetohydrodynamics, is a theory that assumes thermodynamic equilibrium. So there's just one temperature in the system, which is the gas. And so if one is being formal about it, all of these models based on fluid theory with a single temperature are formally invalid if you try to apply them to EHT sources. And I would say they're invalid sort of for two separate reasons that it's useful to distinguish between. And one is dynamics and one is thermodynamics. So the dynamical reason that they're invalid is because the system isn't a fluid, it's a collisionless plasma, and one really should describe it using kinetic theory, not fluid theory. So the analogy would be that we don't today really describe stars in galaxies as a fluid that have a single isotropic velocity dispersion. That model of stars is not very accurate. Instead, we use n-body or kinetic theory to describe the stellar dynamics of galaxies. And that's because stars are a collisionless system. Gravitational scattering is generally not very fast in astrophysical environments. So that's the dynamical reason one would be a little nervous about the techniques that are being used to model EHT sources as fluids. And the other reason I would say is essentially thermodynamics, which is this reason that GRMHD just gives us one temperature, which is the temperature of the gas, but it doesn't tell us what's the electron temperature and what's the proton temperature. And it also doesn't tell us, is the plasma actually in thermal equilibrium in the sense of having a Maxwellian distribution function, or are there significant deviations from a Maxwellian distribution function? And if you want to model synchrotron radiation seen by the EHT is radiation produced by relativistic electrons. So what you care about then is the electron temperature, and in more detail, you care about the electron distribution function. Is it a power law? Is it a Maxwellian? Is it something else? And so to go back to the energy flow that I introduced earlier, What we really want to know in this environment is we want to know, how does the energy that's tapped, the gravitational energy that's tapped by magnetic fields, how does that go separately into thermal energy of the electrons, thermal energy of the protons, or in even more detail, how does that shape the distribution function of electrons as a function of electron Lorentz factor, electron momentum, or the proton distribution function? And it's the electrons, because they're lighter, that produce most of the radiation. So we care in particular about energy flow in sort of the left part of the diagram. So what I want to do now is I want to sort of take you through the state of the art in understanding kind of what the questions are in this dynamical uncertainty I've introduced and this thermodynamic uncertainty, and how to think about them in the context of EHT sources. So I'll first talk a little bit about dynamics, and then I'll talk a bit more about thermodynamics. So the dynamical question is really the question of whether all the beautiful work using GRMHD or MHD on accretion disk dynamics is applicable to these low collisionality plasmas, and what the error might be in using a fluid theory instead of kinetic theory. And the state of the art on trying to resolve this question is to actually use kinetic theory to try to model what's going on in accretion disks around compact objects. That's a very challenging problem, primarily challenging numerically. It's not that challenging conceptually. We know what the underlying equations are. You want to solve the Vlasov equation for the full distribution function of ions and electrons. And we even know how to do this in general relativity. There's been work in just the last year or so solving, kind of writing down the kinetic theory for GR. The challenge really is numerical, is that once you start solving for the full distribution function, it becomes a numerically very challenging problem. And I would say, there's been a variety of different work on this. I'm going to emphasize the work that I think has in some ways been the most definitive. And that has been work that solves for the full distribution function of the ions, but it treats the electrons as a fluid. And the reason for doing that is that it's already challenging enough numerically to focus on the kinetic theory of the ions. Adding the electrons, which have a different temperature, which have different Larmor radii that you have to resolve, is quite challenging numerically. And so focusing one's effort on the kinetic theory of the ions, which after all dominate the mass density, dominate the momentum density of the plasma, dominate the rotational energy that is the fundamental energy source, that's actually a pretty good starting place. And most of the work that's been done on this is not global simulations of material around a black hole, but it's actually local shearing box simulations, where, as shown in this sort of schematic diagram, you study a patch of the disk rather than the full plasma in the full space-time of a black hole. And again, this is primarily because doing this local calculation is already quite numerically challenging. And in particular, it's challenging to get a separation of scales between sort of the size of the accretion disk, the upper wedge here, and the small scales like the Larmor radius of the protons, the Debye length of the protons, things like that. There's a question, if you wanted to resolve electron scales, what would the relevant scales have to be? Do you need to go down to the electron Debye length, or is the skin depth enough? I think the skin depth and the Larmor radius are probably enough, and that seems to be the case based on the work that has been done. the challenge is that getting physical scale separation between the electron normal radius, say, and the proton normal radius is very computationally challenging. So that's the real sort of technical challenge in including the electrons as well. And I'll talk about some work that's been done along those lines on aspects of this problem. I'll get to that in a few minutes. So the question is, has the kinetic model been studied compared to two temperature GRMHD, and what are the departures? And that's actually what I'll show you sort of on the next slide. It's not compared to two temperature GRMHD, but it is compared to MHD. So what I'm showing you here is work that Matt Kuntz did a few years ago, and this built really on pioneering work that Riquelme and Hoshino did earlier, which is studying shearing box simulations of the growth and saturation of turbulence in accretion disks due to the magnetorotational instability. So the upper panel shows you magnetic field energy as a function of time, the different components of the magnetic field energy. The bottom shows you the angular momentum transport due to different stresses that are responsible for angular momentum transport. So there's the Maxwell stress, transport due to magnetic fields. The total stress is the black, the Maxwell stress is the orangish, the Reynolds stress, the turbulent contribution is the yellow. And if I didn't tell you that these were kinetic simulations, and if I instead just showed you this simulation of the saturation of the MRI, the level of turbulence in the disk, the level of angular momentum transport, the so-called alpha parameter in accretion disk theory, right? You would not be able to know that these simulations were kinetic theory as opposed to MHD, a fluid theory. So in that respect, the exponential growth and saturation of turbulence in kinetic theory simulations is actually remarkably similar to what's seen in fluid simulations. One interesting departure that there's still work to try to understand why it's the case and what it might mean is that the distribution function, which is the ion distribution function in this case, is not a Maxwellian. So this is the distribution function as a function of energy for the ions in the simulation. In the saturated state, after the instability has grown and reached saturation, the blue dotted line here is a Maxwellian, and the simulation is shown with the solid line here. And the distribution function here is much better fit with what's called a kappa distribution, which is just one generalization of a Maxwellian that has a power law rather than an exponential cutoff. Because where there's a high energy power law rather than an exponential cutoff. So there's a question of, in 2D, fully kinetic works by Riquelme and others have shown there's a problem. The growth of B causes the plasma to reach an alphane speed close to C, which in principle violates the assumptions of the non-relativistic shearing box. That is correct. That depends on the plasma parameters used to initialize the shearing box in those local kinetic simulations. But you're correct that you can have a situation where the magnetic field amplifies to the point where VA gets comparable to C, which is inconsistent with the non-relativistic shearing box. In these simulations that I'm showing you here, if you kind of convert these into physical units, the alphane speed can be significantly less than the speed of light, so the simulation is self-consistent in that respect. But it's also true that close to a black hole, we expect the alphane speed to be near the speed of light, which is just a statement that you really do need something that's more relativistic like GRMHD rather than a non-relativistic theory, which is what this particular hybrid theory that I'm showing you results of here is. So another question, is there any hope to have a relativistic shearing box? I think the answer is no. And the reason is that the shearing box is actually by construction Galilean invariant. And so it's not consistent with Lorentz transformation. Basically, to set up the shearing box, you do a Galilean transformation from one side of the box to another. And that's not Lorentz invariant. And so having a relativistic version of the shearing box is conceptually problematic. And so we can talk more afterwards if people are interested, but this led to a variety of problems, both conceptual and numerical, in the early work that Riquelme had to do, because those were actually solving relativistic PIC, but using also a Galilean transformation for the shearing box. There's another question about, is there an interpretation of the kappa distribution function? Why is it not Maxwellian? I think there's some interpretation which has to do with what I'll talk about a little later. How is the turbulent energy converted into heat? But in detail, why is this kappa equals 5, which is the particular value that fits the numerical results? And is that generic? Would that apply to any local shearing box kinetic simulation, or is it specific to the plasma parameters used in this simulation? That's still to be determined. Okay. So I want to try to give you a feel for why the kinetic results are so similar to MHD. I think this is actually one of the most important lessons that has come out of the work that's been done, is we have a good physical understanding of why MHD actually works better than you might think in this collisionless environment. And that's very reassuring for all of the fluid models that are used to model EHT sources in other systems. So the first part of the explanation is that in 2 dimensions, the dimensions perpendicular to the local magnetic field, there actually is a very small length scale in the problem, and that's the Larmor radius. Particles gyrate around the magnetic field, and they can't move large distances perpendicular to the magnetic field. And that enforces a fluid-like behavior in the dimensions perpendicular to the magnetic field. The dimension that you sort of have to worry about, where things are particularly collisionless and things can move long distances and look very different from a fluid theory, is the direction along the magnetic field. That's where the long Coulomb mean free path matters. And another consequence of this is that the distribution function is sort of symmetric in the 2 directions perpendicular to the magnetic field. So we don't really have to worry about what is the pressure in the X and Y direction, say B is in the Z direction. All we have to worry about is what is the pressure perpendicular to the magnetic field and parallel to the magnetic field. Because the rapid cyclotron motion enforces what's called gyrotropy, which is the symmetry of the distribution function in the plane perpendicular to the magnetic field. So that's one part of the story about why the fluid theory is a good approximation. The second part of the story, which is equally important, is that it turns out that electromagnetic fluctuations in the plasma, small scale fluctuations due to instabilities, actually scatter particles relatively effectively. And it's these scattering by the magnetic field fluctuations that effectively set a rather small mean free path, small compared to the size of the disk, not small by a lot, but somewhat small compared to the size of the disk. They set the mean free path of particles, not actual Coulomb collisions. And this gets back to a question that was asked earlier about other ways, basically, of having scattering processes. And in particular, there's a whole host of instabilities in collisionless plasmas that tap into differences in the distribution function parallel and perpendicular to the magnetic field. And when the difference in pressure parallel and perpendicular to the magnetic field is larger than roughly the magnetic energy, instabilities set in which scatter the particles and set a finite collisional mean-free path, and in turn enforce isotropy in the distribution function, at least at the level of differences in pressure less than b squared over 8 pi. And just to highlight this, this is actually observed in the solar wind. This is observations in the left in the solar wind taken by satellites. This is the perpendicular to parallel temperature or pressure ratio as a function of beta. And at high beta, so beta is the ratio of gas pressure to magnetic pressure. At high beta, you see these dotted lines here. These are these thresholds of these kinetic instabilities that set in and limit the deviations from thermal equilibrium from an isotropic pressure. And the plasma pressure satisfies those bounds as measured by satellites in the solar wind. And this is also seen in the Kuntz kinetic simulations that I showed you. The distribution function actually remains relatively isotropic, so more fluid-like than you would have thought because of scattering by these kinetic instabilities. And these two properties together kind of make the system behave quite a bit more fluid-like than you would have thought. And that's actually very encouraging for applying fluid theories, GRMHD type theories, to these macroscopically collisionless systems. The question is, are those instabilities going to be dependent on the box size, magnetization, and other parameters in the PIC simulation? That's a great question. That's one of the biggest challenge of trying to apply kinetic theory to these systems. And that's part of what I like about the Kuntz work on this, Matt's work on this, is he achieved the most realistic, although still very far from realistic, separation of scales between the macroscopic scale of the disk and the microscopic length scales like the proton Lommel radius. And we do think that from other work that's been done, that the fact that the pressure is relatively isotropic, as long as you have decent scale separation between the macroscopic length scale, like the size of the disk, and microscopic length scales, like the cyclotron frequency compared to the disk rotation frequency, for instance, as long as there's somewhat decent scale separation between those two, the results of how isotropic the distribution function are pretty independent of scale separation. Okay, so what I want to go to now is I want to talk about this other significant uncertainty in interpreting EHT sources and in modeling them, which is what we want to do is predict the radiation and interpret the radiation that we see. And that means we really need to understand what's going on with the electron temperature and the electron distribution function. But fluid theories only give us one temperature. So how do we do that? How do we get an electron temperature out of a theory that only has a fluid temperature? So what EHT did in their modeling work, just to kind of orient you on what's been done, what they did is they basically assigned in post-processing, they assigned an electron temperature, which was related to the temperature predicted by the GRMHD simulation, and it was related to it by a function that depended on the local strength of the magnetic field. So beta is the ratio of gas to magnetic pressure. And basically the EHT modeling paper said, if beta is small, so if it's magnetically dominated, electron temperature and GRMHD temperature are similar to each other. On the other hand, if beta is large, the bulk of the disk, then the electron temperature is less than the proton temperature by a factor, which is a free parameter that they varied from 1 to 100, something like that. So why would one do this? Well, I think there's both theoretical reasons, but there's also just kind of simple phenomenological reasons of why this is an instructive model to consider. And the reason is that the relative dynamical role of the magnetic field as a function of where you are in the disk. So what plasma beta is, or what sigma is, which is the ratio of the magnetic energy to the rest mass energy of the plasma. These are the quantities that vary the most with where you are in the disk, whether you're near the pole or the midplane of the disk. And the reason is just that the pole is relatively evacuated. There's not much matter there. So that's a very magnetically dominated plasma, low beta, high sigma. While the midplane is, by contrast, relatively gas dominated, high beta, low sigma. And so if you want to introduce a phenomenological model that you can explore different subgrid treatments of the electron temperature, having it vary with beta or sigma, it makes a lot of sense because that's the quantity that varies the most with where you are in the disk. And so you're going to be able to look at the sort of widest range of emission models by having the electron temperature depend on beta or sigma. And that's basically what the EHT did. Some of their models, emission is dominated by the jet, low beta regions, and in some of their models, the emission is dominated by the midplane, high beta models. And those, can give, depending on the kind of properties, you might think those would give similar or different predictions. And it actually turns out that most of those models all predict this characteristic donut-like shape that you've seen in the image for EHT. Some of their other predictions differ, but they're similar in that way. Okay, so that's a phenomenological answer. What if we wanted to answer this theoretically? What if we wanted to know from first principles what sets the electron temperature, what sets the proton temperature, what sets the distribution function? That's what we want to do if we want to understand from first principles the radiation of the plasma. And that's still a hard problem. There's a lot of ongoing work in this. A lot of progress has been made. And I would say there's sort of 3 different physical processes that have achieved most of the attention in terms of thinking about this energy flow. How is the energy in the magnetic field and the turbulence converted into heat and then radiation? The 3 processes for filling in the arrow here that people have thought the most about are energy going via turbulent cascade to small scales where it turns into heat, energy in magnetic field being converted into heat by reconnection, and energy in differential rotation going directly into heat by viscosity, where the scattering due to these kinetic small scale magnetic fluctuations create an effective mean free path L scattering, which means there's effectively a viscosity, mean free path times thermal speed, and that viscosity taps into the differential rotation, producing heating of the plasma. So these 3 processes, there's been a lot of work on, and I'll just very quickly summarize the state of the art in this. So the state of the art in thinking about turbulence in these plasmas is to do fully kinetic simulations of turbulent cascade and try to figure out whether the energy in the turbulent cascade goes to the electrons or goes to the ions. There are both full pick simulations of this, which have electrons and protons. There are hybrid simulations, which have just kinetic ions with fluid electrons. These are some results from recent work that Matt Kuntz and colleagues, in particular Lev Arzamasky and Silvio Cherry, have been doing, looking at turbulent heating as a function of plasma conditions. And what they find is that at low beta, most of the turbulent energy goes to the electrons, and at high beta, most of the turbulent energy goes to the protons in kinetic simulations, which is actually qualitatively consistent with the type of subgrid model used in the EHT results. The work on reconnection, there's also been really beautiful work on reconnection. both reconnection under conditions appropriate for jets, where sigma is high, and reconnection under conditions appropriate for the disk, where sigma is modest. The reconnection results depend not only on the value of sigma, the ratio of the magnetic energy to the rest mass energy, they depend on beta, the ratio of gas to magnetic pressure, and they depend on how strong the ambient magnetic field is that isn't being dissipated. So in reconnection, you can think of it as some of the energy is in the magnetic field that's being dissipated. That's the X component of the magnetic field in this diagram on the left. And some of the energy is in the magnetic field that's in the Z direction, the guide field that's not being dissipated. And whether reconnection mostly heats electrons or protons depends on the strength of that guide field. If the guide field is strong, that's the upper curve here, then most of the energy in reconnection goes into the electrons. If the guide field is weaker, then most of the energy actually goes into the protons. And figuring out whether reconnection in disks has a strong or a weak guide field is still a very active area of research. Okay. Then, as I alluded to,
Eliot,
this is my,
I'm just going to cut in for 1 minute. I actually don't want to interrupt it because we've been getting requests to keep the webinars going a little bit longer. What I do want to say is if anybody needs to sign off at the hour or just not before the end of the webinar, the survey link is in the chat window. Please take a minute to do that. But if you don't have to sign off, we're going to keep going for another.
And I only have really 2 more slides, so.
Okay.
So, and please do the survey, as Burial said. Thank you for that. So this slide just makes the point that I already stated, that viscous heating, due to effectively a mean-free path due to scattering from these small-scale magnetic fluctuations, this is actually a very important source of heating, we think, in these disks. And the way this has been diagnosed is in simulations that explicitly have viscosity, resistivity, and that distinguish between viscosity along the magnetic field, which is very large because there's a big mean free path along the magnetic field. That's anisotropic viscosity in this slide, and viscosity perpendicular to the magnetic field, which is small because of the small Larmor radius. Simulations that include all of these ingredients so you can disentangle what heating is what, find that over half of the heating at high Reynolds number, when you have well-resolved turbulence, over half of the heating is due to this anisotropic viscosity, this long mean-free path along the magnetic field. And that actually operates for both protons and electrons, and preferentially heats the protons by a modest amount for reasons that I can get into if people are interested. So where does that leave us in thinking about what type of subgrid models we should use? Well, I described some of the theoretical work, which actually provides at least a little bit of motivation for a prescription that might depend on plasma beta. That depends, though, on whether you think most of the reconnection has a strong guide field or doesn't have a strong guide field, which, as I'll mention, is still something we don't have a full answer for. So I think if I were to be completely honest, I would say that the jury is really still out on what is the best subgrid model to use in interpreting and modeling EHT sources. I think the model that the EHT is using now has the advantage that it's quite flexible and it allows one to light up either the jet or the bulk of the disk or both. And it's very useful in thinking about the uncertainties in interpreting the EHT results to consider both of those possibilities and see whether or not they produce different predictions and predictions that can be distinguished. Because if they can be distinguished, then maybe we can infer observationally whether most of the emission is coming from the jet, high sigma, low beta regions, or the bulk of the matter, high beta, low sigma regions. And I think that's a great challenge for ongoing EHT modeling and interpretation. Okay, so I'll skip a couple things. Okay, and just end with where are some of the areas where we can make progress in. And I already alluded to the observational progress. I think there are real possibilities with EHT, especially with polarimetry, for disentangling whether most of the emission is coming sort of from the jet, the high sigma regions, or the disk, the low sigma regions. And that will provide, I think, very important insight into the thermodynamics of these plasmas around black holes, into kind of the microphysics of how the heating operates and where the electrons are the hottest. On the theoretical side, I would say our progress can sort of be divided into what you might call macro, micro, and mesoscale. Microscale is the work I described to you using kinetic theory to try to figure out how much heating does turbulence produce, what is the distribution function that turbulence produces, how much heating does reconnection produce, what is the distribution function that reconnection produces. And there's been really impressive progress on this, and that progress is continuing. I think there are interesting questions of whether global kinetic simulations of disks will produce any surprises relative to fluid simulations. There are now models for doing GRMHD kinetic theory. And so I think we'll have some beginning answers to this in the next few years. That's sort of microscale progress. Macroscale progress is really better understanding in global simulations of disks how much of the heating happens by what channel, how much happens by what one might call viscosity or resistivity, or even more broadly, diagnosing where in the accretion disk most of the heating happens, forgetting about whether it's heating due to dissipation of kinetic energy or magnetic energy, but just where is most of the heating, where does most of the temperature increase happen in the simulation, and is that converged with resolution, for example? This is particularly challenging in what are called magnetically arrested simulations. These are the simulations with very strong jets that we think are likely important for systems like M87, and that may well be important for systems like the Galactic Center as well. They're important for M87 because M87 we think has a strong jet. So we think these simulations with strong magnetic fields and strong jets are particularly appropriate there. And the challenge in those simulations is just that the thermodynamics, the density and temperature of the plasma are harder to model because the magnetic field is so overwhelmingly the dominant energy in the system. And then the last area where I would say there's progress needed, and I would actually argue that this is the area where we need the most progress, is what I might call mesoscale, which is really understanding the connection between the sort of idealized reconnection and turbulence simulations I've shown you here and the macroscopic accretion disk modeling. This kind of simulation, a global simulation of an accretion disk around a black hole. Namely, if you take a little patch of that global simulation, can you actually diagnose how much of the heating in that patch is due to what you would call a turbulent cascade versus reconnection? And if it's reconnection, can you diagnose what the guide field is in the reconnection that's important for understanding how much electron versus proton heating there is? And this is the part of the problem that I actually think there's been the least work on. The mapping between the large scale simulations and the smaller scale kinetic simulations to know how to better incorporate our microscopic understanding into our macroscopic model. Okay, I'll end there. Thanks for your questions and patience. And I hope this gives you a good feel for some of the state of the art and some of the uncertainties in modeling the sort of plasma physics relevant to EHT sources. And I'm happy to take any other questions that you have. And please do, if you haven't done so already, please do take the survey at the end. Thanks.
Thank you very much, Eliot, for not only giving an overview of all the progress that has happened, but also the challenges that still lie ahead and what uncertainties we expect and observables coming from those basic physics at these three scales that you're talking about. We had lots of great questions during the webinar, but please feel free to ask a couple more. Again, you can use the chat window or the Q&A, and Eliot has been taking them. Anything that has not been answered yet?
So the question is, have machine learning and model reduction been employed to connect kinetic and GRMHD simulations in one? Not to the best of my knowledge. I think that, so the technique that I know has been used not yet in accretion disks, but in other areas of plasma physics, for instance, in modeling aspects of the Earth's magnetosphere, is where you actually solve different equations in different parts of the domain. You might solve a fluid theory for the global system, and then you might solve kinetic theory in a current sheet to describe the reconnection. And I think that would be a way, an explicit way of trying to bridge the macro and micro scales that might be insightful for comparison to other types of models. But I think, as I alluded to, I think this is an area where there's a lot of work still needed. There's another question, are fluid models with non-isotropic pressures and temperatures relevant or useful? That's something that I didn't get into, but there's actually been a fair amount of work on that, where one actually evolves a pressure tensor, including models for kind of subgrid models for scattering by microinstabilities, including models for heat conduction along the magnetic field. And those models have actually been quite useful. I think they've been quite useful primarily for reinforcing the conclusion that kinetic theory models and these more sophisticated fluid models are actually rather similar to MHD in their predictions for macroscopic accretion disk properties. And so they've helped support this conclusion that, at least for global dynamics, thinking about utilizing GRMHD models really is a good starting point, and that the biggest uncertainty is probably not the kinetic theory of the dynamics, but it's the kinetic theory of the thermodynamics, or it's things like, is there a large scale magnetic field and do we have a MAD or not? That is probably a bigger dynamical uncertainty than whether the pressure tensor is exactly isotropic. Are there kinetic instabilities which don't arise in the fluid approximation? Yes, there are many kinetic instabilities that don't arise in the fluid approximation. Even the fluid instability that does arrive in the anisotropic pressure fluid theory, the fire hose instability, it turns out there's a kinetic version of the fire hose instability that's more important than the fluid one. So when one does these fluid models with non-isotropic pressures, one really still has to include subgrid models that describe some of how the perpendicular and pressure evolve and how they get translated into one another by pitch angle scattering, by instability.
Let's take one last question from Daryl Seligman.
So there's another question, are there other ways to compare MHD simulations with kinetic 6D simulations to figure out what is trustworthy and not in MHD assumptions? I think that's a great question. And That's part of what I actually have in mind when I'm thinking about this mesoscale that I alluded to. I think what would be extremely useful would be to take kinetic theory simulations and fluid simulations and try to compare the dissipation in them. And even to start, forget about the question of electron versus proton dissipation and just ask the question of where is the dissipation happening? How spatially intermittent is it? Is it mostly in current sheets? Is it mostly volume filling? Things like that, and get at the question of whether the fluid theory can provide a useful proxy for where the heating is happening. I think that, I fear that the answer will be probably not, but I think that's an area where we could definitely use more work, and where probably there will be more interesting differences than just comparing kind of really volume average things like total heating, total magnetic energy, total Maxwell stress, which is what I focused on in the description that I gave. So good question.
You're referring to non-ideal MHD in this case, right? You're not talking about numerical dissipation.
Yeah, I mean, I think one could either do non-ideal MHD or one could do these post-processing techniques where you post-process ideal MHD to figure out where the dissipation happens.
The regions. Excellent. Thank you again, Eliot. And just a quick reminder, our next webinar is on November 24th. Come and hear about Kerr black holes and beyond. Professor Emanuele Berti is going to tell us about how we can test the Kerr metric using the HD and what we know about metrics of black holes. So thank you again, and see you next time.
Thanks, everyone, and thanks for the good questions. Bye.
Okay, I think we can also
All right.
wrap
Great.
up. Thanks, Eliot.
Yeah, sure. That was fun.
Bye.